Hi everyone, in this talk, I'm going to introduce our gradient recovery work on search-based software testing. This is a joint work of National University of Singapore, Singapore Management University, University of Pao Seoul, and Xi'an Jiao Tong University. Search-based software testing, or SBST, regards software testing research as an optimization problem, which requires defining an optimization goal, evaluating the fitness of the solutions, and maintaining solutions for approaching the goal. Similarly, SBST has an optimization goal of generating tests to cover a title branch in the program, a measurement to evaluate how far a generated test is away from covering the branch, and a set of mutations to derive new tests closer to cover the title branch. Here is an example where the optimization goal is to generate tests to cover the condition in red. That is, we aim to generate a test to exercise a branch condition where the absolute value of x is equal to 123. A random solution might generate a test such as a equal to 0 and b equal to 0. SBST approaches usually use a measurement called the branch distance to evaluate how far a given test is away from covering the branch. In this example, the branch distance is defined as the absolute value of the difference between two operands in this condition. Thus, the branch distance is calculated as the absolute value of the difference of 0 and 123, that is 123. The less the branch distance, the closer a test is to cover the title branch. More details of the branch distance can be referred in this paper. Based on the branch distance, we can see that a better solution can be a equals to 0 and b equals 100. It is because its branch distance is 23, which is smaller than 123. Keeping mutating this test, SBST allows us to finally find a test whose branch distance is 0. Once 0 branch distance is achieved, we then have a test covering the title branch. In this process, the measurement of the branch distance provides a gradient, allowing us to gradually change from a solution of 0, 0 to the solution of 2300. SBST has proved this practical in many scenarios. However, if we would like to use the same approach to cover this condition, the measurement of the branch distance can no longer work. When we calculate the branch distance in this red condition, which checks the Boolean return value of a method call, the branch distance can be either 0 or 1, as the operand of this condition is either true or false. With gradient, without gradient, search-based testing degrades to random testing. We can only satisfy the conditions by luck. Given the condition, if one of the operands depends on the return value of a method with a Boolean return value, we say that an interprocedural flat problem happens. When interprocedural flat problems happens, SBST usually degrades to random testing. The rationale of our solution is simple. Once we detect interprocedural flat problems, we further investigate the invoked flat method and identify the branch inside, which can return the required flat. If its branch distance has gradient, we use this branch distance to replace the branch distance of the flagged condition. Thus, the gradient can be recovered. In practice, we usually normalize the branch distance between 0 and 1. However, there are 3 challenges to recover the gradients for interprocedural flat problem. The first is multi-pass problem. The invoked flat method may have many branches to return the required flat. Each branch has its own branch distance. How can we choose them? The second is the cascade interprocedural flat problems. There can be another interprocedural problems in the invoked flat method. We need to handle cascade interprocedural flat problems in practice. The third is call and iteration context problem. If a flat method is called in the loop or called in many call sites, the branch for the required flat can have multiple branch distance. Each iteration or call site can derive a new branch distance. Here is an example. Given the input of array keys equals 0, 1, the loop has 2 iterations. In each iteration, the method check value is executed in a different way. In the first iteration, the execution goes through the first and the third condition in the required for the required flag. In the second iteration, the execution goes through the first and the second conditions for the required flag. Different execution leads to different branch distance to reach the required flag. Therefore, which branch distance should we use in such a case? Note that the both problems can cohappen for an individual method suffering from the interprocedural flag problem. In this work, we proposed a graph walking aggregation algorithm to address the challenges of multi-path problems and cascade interprocedural flag problems. Moreover, we calculated context-sensitive branch distance to address the challenges of call and iteration context problem. When an interprocedural flag happens, the invoker method is called the flag method. Each flag method can have a few required flags. As long as those return instruction is executed, the interprocedural flag can be satisfied. Moreover, we call the branch guarding required flag as required branch. We also record the trace of the executed branch towards the required branch. As a result, each branch distance will have call context and iteration context. In this example, it indicates that the branch distance of 1.99 happens under the call context of example and check value method. Here, the method check value is called in the call side of the line 2 in the method example. By tracking the call and iteration context, we distinguish different branch distance for the same required branch. Then we can aggregate those branch distance to recover gradients later. Based on the collected contextual branch distance, we develop a graph walking algorithm to aggregate the branch distance of each required flag. The idea is that when we detect interprocedural flag problem, we statically walk through the cascade call graph and their control flow graph in each call to find all the required flags and aggregate their branch distance back to the interprocedural flag. Here is an example. The target method call a flag method check value, and the method check value further call the method is special. The first step is to identify all the required branches in the flag method. Then we assign the contextual branch distance for each required branch. Note that the required branch can have multiple contexts, thus they may have multiple branch distance. Next, we aggregate multiple branch distance into one branch distance. I will explain more aggregation details later. However, some required flags can further involve a new interprocedural flag problem. In this case, we recursively identify their required flags and investigate the contextual branch distance of their corresponding required branches. Note that in this process, we work through the call graph and the control flow graph of each method call. When finding a new interprocedural flag problem happens, we will walk into the control flow graph of the flag method. Thus, we can also record its call side before walking into its control flow graph. When checking a required branch, we now already have the walking path from the target method to its flag method. We only use the branch distance with the context aligning with the walking path. In this example, the method example should call the method check value at the call side of line 2, and the method check value should call the line method especially at line 5. We only use this branch distance. We only use the branch distance with such call context. After investigating all the contextual branch distance, we will further aggregate the branch distance from multiple passes. In this example, we will aggregate the branch distance from line 1 and line 2 in the method isSpecial. Then we propagated the aggregated branch distance back to the initial interprocedural flag method. By this means, the original Boolean flag will be replaced with a continuous value with gradients, allowing us to facilitate SBST effectively. Here are a few tips for our graph walking aggregation algorithm. The first tip is that without distinguish contextual distance for different call sites or iteration, the aggregation process can confuse some uncovered branch distance as covered branch. As a result, the aggregated branch distance becomes misleading. The second tip is that our aggregation from multiple passes or multiple branch contacts need to satisfy the Boolean property. First, when we are aggregating multiple branch distance, if one branch distance is close to 0, the overall aggregated value should be also approach 0. Second, the aggregated branch should be more sensitive to smaller distance. In general, the smaller the distance, the more promising is corresponding required branch. Therefore, we should give more priority to those required branch. Mathematically, the derivative of the aggregation function towards the distance vi should be anti-monotonic to vi. Given the limitation of the presentation time, the interested audience can refer to our paper for more justification and details. We implement our approach on top of EVA-Suite framework. We name it EVA-Suite for Interprocedural Flag. In our experiment, we compared our approach with EVA-Suite as was baseline. We selected 807 Java methods from 150 open source projects. From those projects, there are 9.3K methods suffering from interprocedural flag problems. In this experiment, we removed some bias method. For example, some interprocedural flag method cannot be instrumented, such as .equals method in JDK library. We also removed some title methods that have complicated objects. EVA-Suite cannot construct tests to create such an objects. Both EVA-Suite and EVA-if will achieve 0 coverage on those methods. Therefore, we remove them for a meaningful evaluation. After removing those methods, we have 807 methods left for this experiment. We run each method with EVA-Suite and EVA-if for 100 seconds for 10 times. Here is the experiment result. First, we observe that 11.8% methods in all the projects suffer from interprocedural problems. It means that such a problem is prevalent and inferential, and this problem is inferential to the effect of search-based software testing work. Second, we can see that EVA-if outperform EVA-Suite in methods with interprocedural flags. We divide the methods in the following 5 scenarios, where first, EVA-if has better coverage than EVA-Suite. Second, EVA-if has equal coverage with EVA-if, but uses less time budget. Third, EVA-if has equal coverage with EVA-if and uses the same time budget. Fourth, EVA-if has equal coverage with EVA-Suite, but uses more time budget. Last, EVA-if has worse coverage than EVA-Suite. We can see that EVA-if improves the coverage in a large number of methods. Moreover, the overall advantage is statistically significant. We observe that EVA-if may incur more runtime overhead. The reason is that it requires more instrumentation to record the contextual sensitive branch distance. We look into the methods where EVA-if does not improve EVA-Suite. The major reason lies in two folds. The first is that some interprocedural flag is trivial, which can be covered by random testing. Therefore, EVA-if has the same performance with EVA-Suite. The second is that the larger runtime overhead sometimes impair the runtime performance of EVA-if. Here is an example. The interprocedural flag is guarded by a normal branch. In the normal branch, EVA-if has an advantage to search to equal string as it spends less time to generate individual tests. Therefore, it can find the solution faster. In this example, EVA-if haven't covered the first branch within the time budget. Thus, EVA-if outperforms EVA-if. In this case, however, we observe that EVA-if can outperform EVA-Suite as long as we given the longer time budget to 200 seconds. Here is the takeaways of this talk. In this work, we introduce a gradient recovery approach to address interprocedural flag problems in SBST. We developed 2 techniques to this end. We have context-sensitive branch distance to address call and iteration context problems, and we have graph working algorithm to address the multiple path problems and a cascading to procedure flat problem. Based on experiment, we show the effectiveness of approach. Our observation on experimental results show that our approach required more instrumentations for recovering gradients, which can be regarded as a strategy to trade the runtime overhead for more gradient information for testing the efficiency. A more promising improvement of our work is to understand when even if can outperform even sweet and vice versa. Thus, we can pursue a hybrid approach, keeping a low runtime overhead while still having necessary gradient information to improve the testing efficiency. That is all my talk, and I'm happy to help your question.